So this lecture is going to be about chapter 9, which is population growth. Population growth can actually describe an increase in the population or a decrease in the population. So I understand it seems as though we're only would be talking about population increases because that's what growth seems to imply to me. But actually, um, population growth can describe a population increasing in number or decreasing in number. So what processes increase the population size, which processes decrease the population size? And we're also going to talk about briefly the difference between an open population and a closed population. So the basic things that increase, well, I suppose really the only things that increase a population are births, organisms being born, and immigration. So remember, immigration, organisms coming into the population. The things that decrease a population are deaths and emigration, or things exiting a population. So an open population has migrants either coming in or going out from it. Okay? Whereas a closed population, which tend to be more idealized systems, do not have any kind of migration, or it's at a level that's so low that it doesn't really influence population growth. So maybe you lose 5 organisms to immigration, but you get 5 back to immigration. Okay, and I know I'm saying those, they sound very different. You should know that for the test. The immigration with an I is organisms coming in, like entering, like in, and the immigration with an E is organisms exiting. Anyway, open populations have migrants, closed populations do not have migrants, or it's a level that it doesn't have an influence. So here's a nice little diagram that shows you population size is a function of births and immigration and emigration and deaths. Okay, those are the 4 factors that are influencing the population size here. So let's do a quick example. We're going to be looking at a population of organisms with a fairly simple life cycle. These are hydra. These things reproduce or can reproduce by asexual budding. So we're going to assume that it's all asexual budding. We're also going to assume that organisms are having 1 offspring at a time. They're not having multiple. And asexual budding, by the way, means that as few as 1 hydra can continue a population because it's asexual. So a few more terms here. N is the number of individuals in a population, and T is a time. So N of T is the number of individuals in a population at a particular time. In this case, we're going to be looking at days. So here, day 0, there are 100 organisms here. And by the way, the time period doesn't have to be days. It would make less sense to look at human beings in this way. So like, let's say we were looking at the population of Modesto. Between day 0, the day we start, let's say there's 300,000 people living there, and day 1, the difference is going to be pretty trivial, right? Maybe some people will die, maybe some people will be born, but it's not going to be that big of a deal. The point I'm trying to make here is different populations can use different time frames. In this case, though, we're just using days. Other assumptions that we're making is that there's lots of food and lots of space, so those are not going to be our limiting factors for this population. So how will this population change over time? Again, this is a closed population. It's an aquarium, so no migration is happening. Budding is going to produce new hydra, which is our births, and some hydra are going to die from old age or because bad luck or whatever it happens to be, maybe disease. So for this population, we are having 40 hydra born, and we're having 10 hydra die. So how do we calculate our population size? Let's switch over to this. How are we going to calculate our population size? So N of 0, write it nice and big for you guys, is equal to 100 organisms. So that's how many organisms we start out with the first day that we're looking at these guys. Our birth rate, not our birth rate, but the number of organisms born is going to be equal to 40, and the number of organisms that die is going to be equal to 10. Right? So how do we figure out how many organisms are around on after 1 day? So n of 1. The way that we're going to do this is we're going to say n of 1 is equal to n of 0 plus the number of organisms that are born minus the number of organisms that die. And hopefully this is somewhat intuitive to you, but we'll plug these numbers in and we'll see what this actually looks like. So n of 1 is equal to 100 organisms. I'm just substituting in because I know I started with 100. And so what are we going to add to this? Well, we're going to add the number of organisms that were born. So n of 100, so we're going to add 40. And we have one more thing we need to do in this case, which is subtract the number of organisms that died. So n of 100 plus 40 minus 10, which means on day 1, we have 130 hydra. We have 130 hydra on day 1. So small. So how do we calculate the population size of day 1? Well, it's the number at day 0 plus the number that are born, subtract the number that die. So just like we just did, n of 0 is 100. There are 40 births and 10 deaths, which leaves us with 130 organisms. So now, though, the problem becomes slightly more complicated. How do we calculate population size at the end of day 2? Can we use the same number of births and can we use the same number of deaths? And the answer to that question is no, we cannot. You can't just keep on assuming that 40 are going to die, or 40 are going to be born and 10 are going to die, because there are more organisms around. It's kind of like if you have a population of 10 people, the growth rate of that population is going to look significantly different than if you had a population of 10,000 people or 1 million people, right? So the way that we do this is by calculating the per capita death rate. Okay, the per capita death rate is just the number that die, or I'm sorry, the number that are born on the first day divided by the number that were there on the first day. So if we had 40 organisms born, our birth rate is 0.4. And hopefully that makes some intuitive sense to you, because 40 were born and we started with this 100 here. So our birth rate is going to be equal to 0.4. Now, how can we calculate or how can we determine the per capita death rate? And I'm sure it's somewhat intuitive to you, but we're going to take the number that die and we're going to divide it by the total number that are there. So in this case, our death rate is equal to 0.1. And if we assume that these are constant relative to the number of individuals we have, we can predict the population's growth rate over time, regardless of population size. So it doesn't matter if you're looking at 100 hydra or if you're looking at 1,000 hydra, you can actually predict what these things are going to look like through time. So how would you determine the size of hydra after 1 day or after 2? We've already done it for 1 day. And you know what? I'm going to go back to the whiteboard here for a minute. I think that's wise. Let's see. Okay. So we have our number for day 1, which is 130. How do we figure out our number now for day 2? How do we figure out our number for day 2? We've calculated our birth rate, which is equal to 40 out of 100, which is equal to 0.4. And we've calculated our death rate, which is equal to 10 out of 100, or 0.1. So now let's calculate, let's see if we can figure out the number of individuals we're going to have at day 2. We don't need this anymore. I'm going to go ahead and just change this. So there we have it. Day 1, we have 130 individuals. And what we're going to do now is, in order to calculate the number at day 2, this is equal to the number at day, let me start over here actually, give myself some more space. So the number at day 2 is equal to the number at day 1 plus the number at day 1 times our birth rate plus the number at day 1 times our death rate. I'm sorry, this should actually be minus. So this might look like some complicated-ish math, but I promise you it's not actually too bad. So let's see if we can plug some numbers in and see if we can figure out how this is supposed to work. So how many hydrogen we have at day 2? Well, that's going to be equal to N of 1 is 130 plus 130 times our birth rate, which we calculated to be 0.4, minus 130 times our death rate, which we calculated to be 0.1. Okay. And let me see here. So let's calculate this out. We're going to say 130 times 0.4. So N of 2 is equal to 130 plus this number calculates out to be 52. This number calculates out to be 13. And let me just finish this math up. So the number at day 2 is equal to 169 individuals. Let's run that one more time, or not do it one more time, but let's calculate the number at day 3 just to make sure that this is all sort of crystal clear to everybody. So I'm going to hold on to this number, and I don't think I need this math anymore. I don't need any of this stuff anymore, all of that. So we're just going to change this to our number at day 2 is 169. So then how do we go about calculating the number at day 3? Well, the number at day 3 is equal to the number we had the day before plus the number we had at the day before times our birth rate plus the number we had the day before, minus the number we had the day before times our death rate. So how many we started with? Our births minus our deaths. And notice that each of these numbers is going to change depending on the size of our population. So let me just crunch those numbers really quick. Or actually, I'll just transfer these down. I'm going to say 169 plus 169 times 0.4 minus 169 times 0.1. And I'm actually going to get rid of our birth and death rates. I don't need them right now. So let's see here. 169 times 0.4 is 67.6. 16.9. All right, let's see what we get. 169 plus 67.6 minus 16.9. At day 3, we have 219.7, or we could call this, we have about 220. That's our answer. So we're going to do another example of this, but hopefully this makes sense. The basic formula is the number you had the day before plus the births minus the deaths. So when populations follow this sort of growth pattern, and don't worry about these deltas, I told you guys I wasn't going to make you do calculus, so don't worry about that. But these represent these exponential population growth curves, which look like this one. Okay, and we're going to talk about later on some populations that you know of, that you probably live in, that showcase this kind of exponential growth and why this can potentially be a problem. So let's look at another example here. There's a population of 100 shrews on an island, and shrews have a gestational period of to a few months typically, well, a month typically, but anywho, in this case, we're looking at a 6-month period. 150 shrews were born out of this 1,000, and 50 shrews died. So the problem here is, can we calculate the per capita death rate? Can we calculate the per capita birth rate? And what is the population size at day 1? And what is the population size at day 2? So let's do this. Go back to the board here for a second. So what is n of 0? N of 0, we started with 1,000. We started with 1,000 shrews. How many were born? Out of this 1,000, there was 150 that were born. I'll make this a lowercase b. How many died? 50 in this case. So how do we go about calculating the per capita death rate and the per capita birth rate? So the per capita birth rate is the number that were born divided by the number that we started with. So we'll say this is equal to 150 divided by 1,000, which is equal to 0.15. Death rate is equal to the number that died divided by the number we started with, which is equal to 0.05. I think I'm doing that math right. Yeah, 0.05. Cool. So we've calculated our birth rate and our death rate. So now let's see if we can go about calculating the number that we would have at day 1. So n of 1 is equal to n of 0 plus n of 0 times birth minus n of 0 times our per capita death rate. So obviously n of 1 is somewhat trivial to calculate. We could just add the number that we had, or the number that were born, and subtract the number that died, which means we're going to have about 1,050 organisms here. Is that how that math works out? Anyway, let's see what happens. So n of 1 is equal to 1,000 plus 1,000 times 0.15 minus 1,000 times 0.05. Am I off the board? Yeah, I'm off the board. Let me try that one more time. Like this. N of 1 is equal to 1,000 plus 1,000 times 0.15 minus 1,000 times 0.05. I'm getting a little messy here, sorry. My comments are where they need to go. Okay, so this is 1,000 plus 150 minus 50, right? So n of 1 is equal to, I think it's 1,100. So after 1 day, we have 1,100 organisms. Cool. So let's see if we can calculate n of 2 now. This map here. So let's write down the formula. N of 2 is equal to n of 1 plus n of 1 times b minus n of 1, this should have been a b, sorry, this is our death rate, minus n of 1 times, n of 1 times d. So n of 2 is equal to our number here, 1100 plus what goes here and what goes here. Well, 1100 goes here. Our birth rate is equal to 0.15. We're going to say minus 1100 times 0.05. And let's see what our math actually looks like. I ran out of space again. Minus 1100.05. Hopefully that's big enough. I think that worked. Well, let's see what we get. We're going to say 1100 times 0.15. 165 minus 1100 times 0.05. 55. So here's our expression for n of 2. So we'll say 1100 plus 165 minus 55. So on day 2, like 1,210. Something like that. I'm not going to give you guys one that's going to be this sort of like arithmetic heavy. What I'll probably do is I'll probably say, hey, you have some population that has 10 organisms in it. Its per capita death rate is 0.1. Its per capita birth rate is 0.2. Let's just do that one actually. Why not? So you'll see something kind of like this on the test. It won't be these numbers. Hey, we have a population of mountain goats. I don't know. It doesn't matter. 10 organisms on day 0. And we're going to say 2 are born. Lowercase, doesn't really matter. And 1 dies. So it's pretty trivial, I think, to calculate day 1, right? Because day 1 is just going to be n of 0 plus births minus deaths, which in this case is going to be 10 plus 2 minus 1, which gives you 11. But let's not be cheesy. Let's actually calculate what these numbers, what these per capita birth and death rates are supposed to look like. So in this case, we'll just make it a capital B. This is going to be 2 out of 10. And this is going to be 1 out of 10, or 0.2 and 0.1. So let's do this again, but plug in our appropriate formula rather than just doing what we're really only going to be able to do for the first day. Since again, these are going to change depending on which numbers we're looking at. So we'll say n of 1 is equal to n of 0 plus n of 0 times birth minus n of 0 times death, or per capita death rate and per capita birth rate. So n of 1 is going to be equal to 10 plus 10 times 0.2 minus 10 times 0.1, which, by the way, gives you the same number. N of 1 equals 11. Same number we got when we just plugged things in. So let's go back, not go back, let's move forward and think about what our equation for day 2 is going to look like. So n of 2 is equal to the number we had the time period before, plus the number we had the time period before, times births, right there, minus the number we had before, times our per capita death rate. So let's see. Let's not forget 11. That's the number we need. So let's plug all these things in. N of 2 is equal to 11 plus 11 times 0.2 minus 11 times 0.1. So let's see what this actually is supposed to look like. 11 times 0.2. I should have been able to do that math in my head. It's okay. 11 plus 2.2 minus 1.1. So the number in theory that we should have at day 2 should be 12.1. Okay, so again, this is going to wind up being exponential. So this number is going to start getting larger and larger, faster and faster. And so if we were going to graph this, it would look something like this. So we'll say time period, or we'll just say generations. I think we were doing deer. So generation 0 here we had 10. So bad. Okay. We had 10, 20. So what's going to happen with these deer is you're going to start with this many, and the population is going to explode exponentially. So if you want a couple of points of extra credit, I think I'll give you 2 points. Just write a quick problem and solve it, or write a quick problem and ask me to solve it if you would like. I might not be able to actually solve it for you, but if you want, I will give you, we'll say, 2 points of extra credit.